Hello, I'm Davinda Gill, an IOP coach, and in this short film we'll be looking at waves for the age group 11 to 14. So in this video we'll be looking at some of the main ideas we would need to introduce when teaching waves. A really good place to start would be to just look at some of the applications of waves, because waves are so vitally important in our everyday lives. We would not be able to communicate without waves. Whenever you're looking at somebody or listening to somebody, it's waves that are being used to transmit that information. Also, you could talk about how waves are used extensively in hospitals. Anybody working with ultrasound scans or x-rays must have a good understanding of how waves travel through different media. Also, when we first start thinking about waves, it might be a good idea to talk about the three-step process. The idea being that with a continuous wave, there has to be a source, a journey that takes place, and then a detector. For example, if you're speaking to your students, the source would be your vocal cords, the journey would be the sound that's transmitted through the air, and then the detector would be the eardrum of the students. Now, in this video, we're just going to focus and develop an understanding of that journey aspect of that three-step process. So here I have a slinky, a relatively simple but an incredibly versatile bit of kit that you can use to demonstrate many of the properties of waves. But the first thing I've really got to highlight is that this is not a toy. It's quite easy for the turns in a slinky to get tangled up, and then it becomes really difficult to use this for demonstrating waves. So when fully stretched, if you let go of it very suddenly, these turns can get tangled up. So if you are going to choose a student to hold the slinky at one end, make sure they are aware of this. Secondly, if your students do ask for you to roll the slinky down the stairs, I would discourage that really, because once again, there is a risk that the turns could get tangled up. And if you really do get the urge, then use one of those toy plastic slinkies. Two other points. Always ensure that the slinky is stretched across the floor or along desk, as you can see here. Do not hold the slinky horizontally or vertically in the air to do this demonstration. And finally, aim to send single pulses along the slinky rather than a continuous travelling wave. This is because the wave and its reflection would interact, producing something called a standing wave, which is not what we want in this case. So in this topic, there are a large number of terms that students need to know and memorise ready for testing exams. So terms like amplitude, wavelength, frequency, period, wave speed, transverse, longitudinal, compression, rarefaction, oscillation. These are all terms students are expected to know. As a teacher, you might need to think carefully about the cognitive load you place on your students, and so perhaps focus on just a handful of these terms when you do your first demonstration. So the first idea here is that a continuous wave transfers energy from one place to another. Secondly, highlight to your students that once the pulse has passed a point, the slinky remains unchanged. So here we have an example of a transverse wave because the coils of the slinky oscillate or vibrate across the direction in which the pulse travels. A marker on a single coil of the slinky, here in blue and yellow, helps students to focus on the movement of an individual coil which models the movement of one molecule of the medium. At this point, you could start a discussion on a Mexican wave perhaps, and how in a stadium the pulse travels around the stadium at right angles to the direction of the spectators throwing their arms up in the air. You can even model this with students in your classroom. Another excellent example of a transverse wave you can make in your classroom is with jelly babies and cocktail sticks. There is a link below this video in IOP Spark if you would like details on how to set up a jelly baby wave machine. So just to summarise, number 1, a continuous wave transfers energy. 2, in a transverse wave, the oscillations are at right angles to the direction of wave travel. And number 3, the medium will remain unchanged once the wave has passed. So the following simulation is available online and has been produced by the PhET team at the University of Colorado. To produce a continuous wave I've clicked on Oscillate on the top left. I've clicked on No End on the top right. I've set the damping to 0, and the tension is halfway between high and low. So let's get the wave to move across the screen. And perhaps the first thing here is just to reinforce this idea that as the wave travels across the screen, the particles themselves oscillate at right angles to the direction of wave travel. It's such a deep and ingrained misconception among students that it may well be worthwhile reinforcing this again and again. This idea that the medium itself does not travel with the disturbance. Now there are three particular descriptions of waves I want to get across with this particular simulation. So let's just look at those in turn. So first, the reference line running through the center of the wave there, the horizontal line, corresponds to the line of zero displacement, or sometimes known as the equilibrium position. The second thing we need to say is that the distance, the vertical distance from this line to the maximum displacement of the particles is called the amplitude of the wave. Now in this example, that is a distance of 1 centimeter. Now some students may think it is the total vertical distance travelled by the particles, but that would indeed be twice the amplitude. And finally, the wavelength. Well, the wavelength is the length of one whole cycle of the wave. So we can measure from the tops of the wave, which are sometimes called peaks or crests, and it would be the distance from one peak to the next peak. Or we can measure from the bottom of the waves, called troughs, and it would be the distance from one trough to the next trough. You can measure from the center of the wave, but do take care here, because where the wave crosses the line of zero displacement to the point where it crosses it again corresponds to only half a wavelength. Now students do need to be very precise when they make measurements of wavelength, and when they label a diagram it is important that the ends of their arrows are in exactly the correct position. And finally, if students are going to determine an accurate value for wavelength, it makes sense to measure the length of several waves and then divide by the total number of waves. Just as an example here, although I've only got 2 waves on the screen here, the length of 2 whole waves corresponds to a distance of 5.0 centimeters. That means the wavelength is 5.0 centimeters divided by 2 waves gives us a wavelength of 2.5 centimeters. We have discussed transverse waves, but another way in which waves can travel is as a longitudinal wave. And the slinky is very good to demonstrate this. As I send a pulse, my hand needs to oscillate in the same direction as the wave travel. The turns of the slinky get close together as the pulse travels along. These regions where the turns are close together are called compressions. That means there must also be regions where the turns are far apart. These are called rarefactions. This lovely simulation can be used to describe and examine longitudinal waves really well. Get your students just to focus on the red dots there. It's quite difficult to see them, so I've highlighted them. Get your students to describe the motion of those red dots. Hopefully, they'll see that although the wave is travelling across the screen from left to right, the particles themselves just vibrate or oscillate backwards and forwards parallel to the direction of energy transfer. Also, let's think about what the terms amplitude and wavelength mean in this context when we apply them to longitudinal waves. Well, the wavelength is just the distance between successive compressions, or indeed successive rarefactions. But amplitude is not simply the distance travelled by the particles, and that's a common misconception students have. Remember, amplitude is the distance from the equilibrium position to the maximum displacement. So it would be half the total distance horizontally that the particles would travel. Here we have 2 oscillating systems, a mass on the end of a spring on the right and a simple pendulum on the left. We can apply the term amplitude here too. It's the maximum displacement of these masses from their equilibrium position. And by equilibrium position, I mean the position of these masses when they've come to rest. So for the pendulum, that would be here. And for the mass on the end of the spring, that would be there. But my main aim of showing you these two demonstrations is because I want to introduce two new terms for wave theory. Period, measured in seconds, and frequency, measured in hertz. So we can define period as the time taken for one complete oscillation. So in this case, what I mean by oscillation is the time taken for the pendulum mass to move from here all the way to the opposite end and back again. That's what we mean by an oscillation. You can talk to your students about how you could determine an accurate value for the time period by measuring the time for, say, 20 or 30 oscillations and then dividing by the number of oscillations. Now, the frequency is defined as the number of oscillations in 1 second. Now, lots of practice here will enable your students to develop a really good understanding of what these two terms mean. So let's look at some examples. Imagine a pendulum with a period of 0.1 seconds. What would be the frequency in this case? So let's think about how we might word this question. A period of 0.1 seconds means our pendulum here takes 1/10 of a second to complete one oscillation. So the question really is, how many oscillations does it manage in 1 second? Well, if it can complete one oscillation in 1/10 of a second, it should be able to manage 10 in 1 second, which would give us a frequency of 10 hertz. We could then go on and use other examples. What if the period was 0.5 of a second? So it took 0.5 of a second to complete one oscillation. Then the pendulum should complete 2 oscillations in 1 second. So the frequency in this case would be 2 hertz. What if the period of our pendulum here was 1 second? Then in that case, the frequency would have to be the same. It'd be 1 hertz. What if the period was, say, 2 seconds? So it took 2 seconds for one complete oscillation. Then the pendulum would only manage half an oscillation in 1 second. And so the frequency in this case would be 0.5 hertz. Finally, we could also ask students about the period if we provide them with the frequency. So what if we had a pendulum with a frequency of 5 hertz? So it completed 5 oscillations in 1 second. Then how long would it take to complete one oscillation? Well, in this case, the answer would be 0.2 seconds. So at this point, your students will hopefully be able to see the link between period and frequency of oscillating systems. So what about waves? Well, the following simulation shows a wave moving across the screen, but just look at the red dot. So that represents the motion of a single particle on the wave. And we'll see the motion is very similar to the mass on the end of the spring that we had earlier. So we can use the same terms. The period is the time taken for one oscillation, and the frequency is the number of oscillations in 1 second. But notice also that the wave moves forward by one whole wavelength in one period. So we can think of the frequency of a wave as the number of waves that pass a point in 1 second. Now, if you are going to use this simulation, then do take a little bit of care, because the two graphs you see below the wave look very similar, but the first one shows how the displacement of a particle varies with time. So a measurement between the two peaks here would be the period of the wave. Whereas in the second graph, well, that's like a snapshot of the wave. So you've got position on the x-axis. A measurement between the two peaks here would be the wavelength of the wave. Also, there is a small mistake that some of you will have noticed. The label on the y-axis should be displacement and not amplitude. So in this final part of the video, I would like to just spend some time talking about superposition. You could maybe start by having two students opposite ends of the classroom, each with a football, and get them to roll the footballs towards each other at the same time. Now, if they do it carefully, the balls will collide and move off in different directions. But compare what happens when we do the same thing with waves. So you could actually use a slinky now and get the students to stretch the slinky across the classroom and at the same time send a pulse. And what we find with pulses here is that they actually pass right through each other. It might be easier if one student sends a transverse pulse and another one a longitudinal pulse, or if both send a transverse pulse, make sure they have the opposite displacement. It might even be useful to get some students to record in slow motion what happens at the point where those waves overlap. So the following simulation is perfect for describing superposition to your students. As you can see on the screen, I've got two peaks. They've both got the same amplitude, and I'm just going to get them to move towards each other. They're going to overlap. So it's just running now. And watch what happens when they overlap. In fact, I'll pause it at the point where they overlap. And you can see the waves have added up. We've ended up with a wave that's got a much bigger amplitude. In fact, it's got twice the amplitude of the individual waves. This is an example of what we call constructive interference. Now, I'm going to continue running this. But now I'm going to send, instead of two peaks, I'm going to send a peak and a trough. And let's see what happens when they overlap. I'll pause it again. And you can clearly see that it's as though the waves have completely cancelled out. This is an example of destructive interference. So how can we give this some context for students to kind of understand what's happening? Well, think of a toy boat on a lake. If the crest of a wave was to travel across the lake, the boat would rise and fall again as the crest passed. But now think about if two crests arrive from opposite directions. At the point where they meet, if the boat was in that position, it would rise even further. But that's not always the case, because if we had a peak and a trough traveling in opposite directions, and at the point where they overlap, and the boat was in that position, the boat would not actually move in the water, even though there's two waves coming towards it. So thank you for watching this video. Please do watch the other videos in the domain program. In particular on waves, we've got the ripple tank for the age group 14 to 16, and also we have interference at advanced level for post 16